All right, so this video is a quick introduction to linear regression. As I like to do, I'm totally mooching the slides from Dr. Scott Thatcher. He actually combined models and linear regression. I have a separate video on models that he has, although he used the same idea of using the model of a car and how you make models simpler and simpler. Anyway, as we talked about in there, statistical models create what he calls a low-dimensional summary of a data set, which I actually think is a great phrase, because the idea is you have all of these dots, and while they're giving you the story, the models that we have summarize it in a way that needs less information than we started with. So on the one hand, that's dangerous because we've lost information, but on the other hand, given that our future information might not look like our past information anyway, summarizing really makes sense and helps us do that. Now, there are two different kinds of models we're going to talk about. Predictive models are ones where we try to predict what's going to happen in the future. And regression, which we're going to talk about here in a second, is totally useful as a predictive model. But it's also interesting as a discovery model where we simply look for patterns in our data. Now, models come in families, and the regression family is actually quite big. So for instance, two that he puts up here are a linear model where we're just going to make lines, and that's what we're going to do in this class. There's also a quadratic model where you make little parabolas here, and that would be kind of fun because now you would be able to use higher order things. It also would allow you to use the stuff you learned in Algebra 2 because, hey, quadratic formula. But you see it has a squared term in it, and that adds complexity to the model. And whether or not it adds useful information is up in the air, but we're gonna, in this class, just talk about linear models. And in fact, in many real cases, you use linear models, and even if your data is quadratic, you instead transform it. You take the square root to turn it into a linear model in order to analyze it more simply, because quadratic models do take way more computational power. So especially for big models, that's important. Now, we're also going to talk about what we call fitted models, which are where we fit the best model to our data. So in this case, we did a little math here, and we got this fitted model. Looks like a linear equation, which hopefully sounds very familiar to you. If we did the quadratic model, you can see it looks like that, and it has this square term on it, so as years of service get bigger, it starts to curve back down. Now, which of those fits the data better is actually a pretty complicated question, and one that we're often going to solve with our eyeballs by looking at graphs rather than looking for some mathematical best answer, because different measures of good models will give you different things. So we're going to talk about simple linear regression here first, which is where we literally have one model with an intercept and one slope, and then an error term. And a model statement is a way of expressing these equations in a theoretical sense. We're then going to come up with a fitted model idea, which is how we're going to calculate the version we're going to have. And again, this idea of error, we're not going to calculate because that's what's left after we've done it. Now, as you remember from algebra class, if the data is perfectly linear, then it's easy to calculate the line, and you can use your equation, rise over run, and solve for it after doing the plugging in. So if your data really is perfectly linear, you probably aren't doing a statistical model because our data is never so pretty as that. In real life, our data is not perfect. And here's a data set Dr. Thatcher likes to use about the price of different Lego sets versus how many pieces they have. And unsurprisingly, pieces with more pieces in them cost more than pieces with fewer. But you also have the complication of branding, and the ones with superheroes or the ones with Batman or whatever is hot at a particular time. Ninjago was hot for a while. Those pieces cost extra, the Harry Potter sets. They would cost more than just the same size model with blank pieces. So we're going to do what we call LeastSquares criterion. And the idea is for each line, we're going to look for how wrong it is, and we're going to look for the line that has the minimum least squared residual. So residuals are just subtracting, so we take the actual value versus the value that we predict, square that, and add them all up. And that calculation, we're just going to find how far our point is from the line, And for each line we could calculate, we're going to find that amount and then look for the best fit by finding the line that has the smallest value for this error equation. And again, there are different kinds of error equations. We could use perpendicular distances. We tend to use these vertical distances because to calculate them, you just subtract how far your answer is off of the other one. For this one, even though mathematically this makes a little bit more sense, you have to use trig because, right, you've now made little right triangles. You can actually also calculate the actual sum of those triangular areas. Now, in a stat class, and maybe you remember from Stat 190 or wherever you took your introductory stat course, calculating this actually wasn't too hard to do with our formula, but if you use different models, there are actually different lines that you would generate. And we're going to use what we call ordinary least squares, which here is OLS. And you can see the lines are only off by a little bit, but that little bit can make a big difference in our prediction model. That idea of squaring it means that we try to avoid really big outliers. That can mean that particular points can have a big difference. And this least squares version actually does have some good examples. It's actually really good for prediction. It seems to do well in practice against real data. And then computationally, it has a couple nice features that mathematicians care about that maybe we in stats don't get too hung up over. But because of that, things work out very nicely. The other thing you might remember from your intro stat course is that there were formulas that you could calculate the slope and the intercept. The slope, actually, this is the formula you have. You might have learned it as R times the ratio of the standard deviations, having to do with z-scores and stuff. But once you have that, then the intercept can just be calculated using simple algebra. And again, we're not going to calculate these by hand at all because we're in a data science class. We're going to have millions of data points, but the formula is literally the same one you would have done in your algebra class or in your introductory statistics class. So I'm going to move away from his slides for a second. I'm going to go to a different example. So here is a data set that I found on the internet, so you know it's true. And it's about the length and weight of 56 fish that were caught in a net in Finland. And I think that's a cool, kind of ridiculous example. And unsurprisingly, in general, longer fish weigh more than shorter fish. And it turns out that this actually is a business problem because fishermen want to collect as many fish as they can. They want to catch as many fish as they can, but it's really hard to weigh fish when you're on the open sea. These are from a lake, so they actually brought them ashore to weigh them. But if you imagine you're out on the open ocean, if you think about how you weigh things, you either use a spring balance like you see at the grocery store, right? And of course, on the open ocean, every time the ship moves up and down, your scale would move up and down. In a chemistry class or in an engineering class, you would use a balance scale. And of course, that doesn't work very well either on the open ocean. So this idea of estimating the weight of fish from the length is actually a super important one. And it's one that fishing vessels and people who care about such things do. If you ever watched any of those shows on the Discovery Channel, you would actually see that they actually measure fish by the length rather than actually weighing them, and then they put them into bins and they use that to calculate how many fish they can catch or how many more days it's going to take them before they go back to shore. So I made a little scatter plot here of our fish, and I used that formula that we had, and actually I calculated down here. This is from my intro stat course when I teach that. And you get the equation like this. So the slope of the line is 35 with rounding, and that equation is actually a pretty nice one. So in general, every centimeter long your fish is, you would expect it to weigh 35 grams more. However, it's sort of weird because the intercept is minus 652 grams. So that would tell you that a fish of 0 length would be expected to weigh minus 652. And if you imagine this line continuing, it would come down here and you would get this negative weight fish. And of course, fish of negative weight would float. And I feel like you would have seen that before if that was a thing. Some nature special would have covered that. So what that tells us is that maybe a linear model isn't a great one for it. And if you look here, you can see that there is sort of a parabolic relationship or something like that. You actually can model it pretty well with 2 lines, which is called a spline model, which is one we won't talk about in this course, but is another way to do it. That said, over here, this model actually works pretty well. And if I said, hey, how much do you think a 35 centimeter fish would weigh? You would take the 35 and you go up, and you go over, and you'd say, oh, I estimate it weighs about 580 grams. And that would be a really helpful model to have. Again, in data science, we're not going to calculate all this. You can see I calculated the means and standard deviations, and I did those formulas like we did there. But this idea of having these slopes can be really helpful as we try to make predictions and make models. We'll later get to multiple regression, where you start to add more and more variables to see if you can get better models by using more than one variable at a time. All right, going back to his slides, because I think he does kind of close it out here pretty well. You know, he's again using this very small 5 Lego sets to predict price. And the slope, we can see that for every piece, we expect it to cost about 8 cents more. So if you think that a Lego piece costs 8 cents, that's a really quick and nice model. However, we know that some Lego pieces are fancier than others. Some are more expensive. The other thing is he has the same problem we had, which is that that negative intercept, it would imply that an empty box would cost minus, right? They're not going to pay you to take an empty box of Legos. So how exactly that works, excuse me, is going to be important. Now, this note here on his slide, which is that we try to stay inside of our model, try to stay inside the data that we have to make predictions, is a good idea. So when you make a prediction inside the range of data you have, we call that interpolating, and that's one idea. When you make a prediction outside, that's called extrapolating, and extrapolating can sometimes be very dangerous. That said, extrapolation is typically what we want to do. So even though we know that it's dangerous and it's worrisome, whenever we're using time as a variable, we're always trying to predict the future. We're not trying to predict the past. We know what happened in the past. But this idea that there's worry about what's going to happen in the future never quite leaves us from here. So here's the equation of the line that was calculated. We got the mean. And we can plug in new numbers. So if someone came along and said, how much would a new piece with 383 pieces cost? He comes along and he predicts it would cost $28.57. And in fact, you know, these residuals are going to be important, and we'll talk about ways to analyze them a little bit later. In R, we're going to use a very easy command to use called LM. And so LM stands for linear model. And to do that, all we have to do is we make our new name and LM, and then we take the name of our predictor variable and this tilde, and then the thing that we think predicts it, comma, where our data comes from. So in this particular example, he was trying to predict salary based on years of service from the salary data set. And then the summary of that, when you do it, spits out a thing that looks like this. It gives you the range of the residuals. Those are how far off they were. You can see if they're far or not far. In this case, they're off by $100,000 and $80,000. So that's a lot in both directions. We get a value for what we think the intercept is. So the idea that a brand new hire would come in at $100,000 and they would expect to have $780 more for each year of service. Notice here's a p-value. This is a t-score. Again, we're not going to talk about those too much in this data science class, but the idea that the null hypothesis that the intercept is 0 has a super tiny p-value for both the intercept and for the slope. So we think there's something going on here, and it does turn out that people who make, people with more years of service would expect to make more money. And that brand new hires wouldn't make $0. That's probably a less interesting value. We can then add the line to our graph very easily. Again, I always forget this, so I get out my ggplot cheat sheet, and stat smooth is the command that we want. And the stats are over here on this column. And you look here, and stat smooth is one of the ideas, and we look for the different methods. And method equals LM is linear model. The one that's actually default, he showed you that one here at the earlier slide. This one is the idea of a low S model, and we'll talk about that a little bit later. But a linear model where you make a straight line is the one that we're typically going to use when we do regression. So you see ggplot, the data set of salaries, then we add the geom point to put the dots on, and then stat smooth adds this smoothing function and the summary statistic that we can then see with the blue line. And like everything else in ggplots, you can fiddle with all of the parameters and stuff to make it different colors or to add it. Notice that it does give you an estimate of the error. And so we'll talk about that a little bit later. But it gives you the best estimate for the line and then an estimate. You can see where it has more points there isn't an error that you can see, because where you have lots of data, the error estimate is very close, but where you have fewer points, it gets wider. All right, so that's a quick introduction to regression, and now we're ready to go in and start looking at how it works with the actual software.